I wanted to try a little bit of a modular approach to making a capacitance discharge welder. I've put together 3 modules for testing. Everything is just tied together with copper bar at this time, making it a little spread out and messy. That will get sorted out in future versions, I hope. Each module is composed of a MOSFET power switchboard, a 0.47 farad capacitor, and a high-powered Schottky diode. The on-state resistance of the switchboard should be less than 0.2 milliohms, so most of the resistance of the module is going to be the ESR of the capacitor. The capacitor choice was a trade-off between ESR and price. The ones I'm using are listed as 9 milliohms and cost a little over $40. To get down to 4 milliohms would have doubled the cost. Here's a schematic of what I'm trying first. There are multiple current paths to the negative capacitor terminal. Most of the current will flow through the main connection to the switch module here. Some current will flow through the connection to the negative charge line here and here. Switch module turn on and off timing skew will cause some of the current, but I believe the prevailing current here will be from the differences in capacitors. All of the MOSFET power switches and driver ICs have come from the same lots, so at this time I don't think I can reliably judge the effect of on and off timing skew. Of course, a current flowing in the negative charge line is going to cause a voltage difference. This is where things get interesting. That difference will be seen on the signal reference and 12-volt reference terminals. So for this to work, the resistance of the charge line between the negative terminals of the capacitors is going to have to be just right. This is a waveform of the 3 negative terminals of the capacitors at switch on time. The yellow trace is the switch bus. While there is only a few hundred millivolts difference, that difference is over just about 8 inches of 14-gauge wire. But that is enough difference, I believe, to make the MOSFET switchboard primarily handle the current through the capacitor it is hooked to. And I think as long as there is not much over 1 volt difference, it will not interfere with the signal to the MOSFET driver IC. While it would be easy to isolate the gate drive to the MOSFET switches, isolating the power to charge the capacitors and power the MOSFETs would be a lot more expensive and complicated, really making the entire modular approach not worth the trouble. The power switchboard has 6 MOSFETs, with each MOSFET having an on resistance of about 1 milliohm. And with the connections to the copper bars being as close to the MOSFETs as possible. The MOSFET driver IC has separate on and off outputs, making it easier to control turn on and turn off slew rates, with the turn off being very important. Interrupting 1,000 amps plus current, even through a very small inductance, if done too fast, can have very serious repercussions. This waveform of turn on shows a little over 2 volts a microsecond slew rate. I may need to slow that down some. The waveform of turn off shows the slew rate is about 0.1 volts a microsecond. That rate isn't causing a problem, but I might manage to increase it a bit to save some energy. The switchboards are controlled by a timing board that can supply a single adjustable on pulse or a double pulse with an adjustable on-off-on timing. Right now the capacitors are just being charged by a bench power supply, as this really is just in the early stages. So even with the complications of a little bit of modularity, I'm not ready to give up on the idea just yet.